Continuing on in our journey of programming a PIC microcontroller in assembler, today we're going to explore another peripheral, specifically the SPI mode of the serial port. And what this will allow us to do is expand the number of digital outputs using this incredibly versatile device, a 594 shift register. Now, if you're just joining me for the first time on this journey of creating this digital illumination system, I highly recommend you go back just a few episodes to when we started our deep dive into PIC microcontrollers, because there is some foundational knowledge that if you skipped over it, a lot of what we're going to cover today is going to be somewhat confusing. But if you're already caught up, perfect. Here's our circuit as we left it last time. There's our power and ground connections over here. We have some connections leading to our programmer over here, and there's our PIC device right in the center. Aside from the necessary components, we have two LEDs here that are going to blink on and off based on timer frequencies that we configured in previous episodes. We have a reset button, which will bring our device into reset if we need to. We have a rotary encoder over here, and a single physical push button switch, along with four LEDs that are connected to RC 0, 1, 2, and 3 that are serving as indicators to let us know what's happening when we turn that rotary encoder or push the button. And on the last episode, it was working wonderfully. Our problem, of course, that with the 6 LEDs that we currently have connected to our PIC microcontroller, it's out of pins. A number of episodes ago, we designed this system with at least 16 discrete levels of intensity, and we need at least 16 indicator LEDs in order for us to know what intensity level it is. And that's why I wanted to use this 594 shift register. You see, what we're doing right now is we've given each indicator LED its own dedicated pin, and so that LED lets us know what's happening on that pin, whether it's a digital high or a digital low. So if all the pins have their own independent signal, then all the indicator LEDs will illuminate based on that signal. That's an example of a parallel output. And the neat thing about this shift register is that it will generate a parallel output using a serial input. And so rather than connecting individual LEDs to the outputs of our microcontroller, we connect those LEDs to the outputs of the shift register, and then use our microcontroller to generate one bit at a time and feed that into the shift register so we can display all that information there. We can use the pinout diagram in the datasheet to help explain this. We can see the 8 parallel output pins on the shift register along with the single serial input pin. So if we connect our microcontroller to that serial input pin, and then set that pin to either a 0 or 1, then send a clock pulse to that shift register. The shift register will then take that data bit and store it in position number 0. Then we can change that data bit to something else, send another clock pulse, and the shift register will then put that bit in position 0 while shifting what was in position 0 to position 1. We keep doing that until we fill all 8 positions, then send a clock pulse to the storage trigger pin. Then the shift register will take those 8 bits and put them directly onto the pins. So we're generating an 8-bit output using only a 3-bit input. In other words, by using 3 pins on our microcontroller, we can independently control 8 different LEDs on this shift register. Going back to our schematic, we can remove these LEDs and their associated resistors, which will free up pins RC0, 1, 2, and 3. Then we can add in our shift register over here, connect 8 LEDs to the outputs of that shift register, and connect the inputs of that shift register to RC0, 1, and 2. Specifically, RC0 is going to send the shift register clock pulses, RC1 is going to send the data bits, and RC2 is going to send the storage register clock pulse. Now let's make the changes on the breadboard by removing all this extra stuff. Then we can attach our shift register to the breadboard and make all its necessary connections, as well as run those leads from RC0, 1, and 2. I'm also going to add another breadboard near the bottom that's going to hold our indicator LEDs, all 8 of them, and then we'll use these leads to connect them to the shift register, keeping it as neat as possible. Now in our code, we can start making changes to the comments to reflect the wiring changes we made. Next, we're going to temporarily disable our button detection code that we created in the last episode, because that code leverages some of the pins that we're now using to send our serial communication to our shift register, and we don't want that button code getting in the way. And the simplest way to do that is simply to disable the interrupt which detects a button press. So we'll change this line of code to only enable the timer 1 interrupt, and then comment out the 2 lines that enable the CCP2 interrupt. Now we need to change the interrupt code that handles the turning of our rotary encoder. We're going to adjust this code to determine which direction the rotary encoder is turning. And then depending on that direction, put either a 0 or 1 on the serial data bit. After placing the data, we'll pulse the shift register clock, and finally trigger the shift register storage. And it works exactly as expected. Turning the rotary encoder one way turns bit 0 on. Turning the rotary encoder the other way turns bit 0 off. And with each turn of that rotary encoder, that bit is shifted down the line. So that demonstrates that our shift register is working. But it's not doing exactly what we want. We want this thing to display 8 bits of data each time, rather than just displaying a single bit of data which slides off the end. Since we can only send a single bit at a time, we're going to define a register that will hold the entire 8-bit value. We'll call it the intensity target, and we'll make sure the value is 0 on initialization. Then we'll prepare a value which will determine the increment each time we turn that rotary encoder. In this case, it'll be 1. Unless the rotary encoder is turned the other way, in which case it'll be -1, or FF. Then we'll add that value to our existing target intensity. Then arm the storage register by clearing it, call a subroutine to send all 8 bits of data, and then trigger the storage register to output that data. Now the purpose of the subroutine is to sequentially send all 8 bits of that register. Now because of the way the shift register works, and how we've wired up our LEDs, we need to send the most significant bit first. And that's where our LSLF, or our logical left shift instruction, is going to come in handy. See, when this instruction is issued, the most significant bit, which is F7, goes into this thing called C. The C refers to a special carry bit in the status register, located right over here. See, once that bit is in the status register, we can evaluate the carry bit and then set or clear the data bit for the serial communication. Then, when we left shift again, the next bit, in this case it would have been bit 6, ends up in the carry bit of the status register, and then we evaluate that and send it off again. Left shift again, then the next bit ends up in the carry register, and so on. We do that 8 times, and before you know it, the entire 8-bit register has been evaluated and sent. And here's what that subroutine looks like. We collect our target intensity value, store it away in a common bank register. I'll get back to what that is in a moment. Then we create a loop counter for each one of our 8 bits and put that in another common bank register. Left shift that register into the status bit, and then we test that status bit and either set or clear the serial data bit, trigger the output clock, and decrement the counter to do it all over again. So let's get to what this CBR thing is. We've already covered what GPR, or general purpose registers, are in previous episodes. It's basically just an 8-bit data holder that's located in the data memory of our microcontroller. Well, the CBR, or common bank register, is almost the same thing with one difference. These general purpose registers that run from address 20 to 6F are different depending on the bank that you're in. But the CBR, or common bank registers, are the same regardless of the bank that you're in. Now this is super useful if you have data in one bank that needs to be transferred to another bank. Now we're not using it for that purpose right now. We're using it for an entirely different reason, and it's more personal, I'd say. See, for me, when I create general purpose registers, I like to give those registers a purpose. And that purpose is generally persistent throughout the entire life of the code. It's just easier for me to kind of mentally organize where I'm putting information. Common bank registers, on the other hand, do not have a defined purpose for my code. I like to keep the scope of their use very, very small, so we're using them temporarily, but my understanding is they're only going to live within the scope of whatever it is that I'm writing. So practically what that means for us is they only live within this subroutine. And I can't expect them to hold on to that value outside of this scope. Now, this is just a personal rule. It's the way I like to code in assembler. You by no means have to do that, nor is that any sort of rule. It's just a way that makes sense to me. Okay, look at that. We are sending discrete 8-bit values to our indicator. Let's take a closer look at the actual signals that are being sent. On the scope, the yellow line is the storage trigger and the blue line are the shift clock pulses. Because I only have 2 leads on my scope, I can only show 2 signals at once. And these 2 signals are the important ones because it tells us how long the entire communication takes. This thing takes just over 80 microseconds to process. And that's based on our current microcontroller speed of about 4 megahertz. It is incredibly quick, which is why this is so incredibly responsive. But remember, in our code, we are manually flipping those bits up and down. And when we got started on today's episode, I did say that we're going to explore a peripheral that can do this for us. So let's leverage it. This is a specific peripheral I'm referring to, the MSSP, or the Host Synchronous Serial Port Module. So why don't they call it the HSSPM? This device has a couple of modes, an SPI and I2C mode. We're going to focus on the SPI mode for now. And the datasheet says that it requires 4 connections. SPI communication is bidirectional, meaning it can send and receive information. We're not interested in receiving information from our shift register. We're only using it as output. So we don't actually need 4, we only need 3. The serial clock, serial data out, and the client select. The client select exists so you can attach multiple devices to the same serial port and use the client select pin to select which device you actually want to connect to. Here's a diagram that illustrates that. For each device, you need a separate SS pin. Now we only have one device, our single 8-bit shift register, so we only need one client select signal. And as luck would have it, the client select signal behaves exactly the same way as our storage trigger signal does on the shift register. And even better, we've already wired it up the right way. RC0, which is the shift register clock, is the same as the SCK or serial clock signal. RC1 is the serial data output, which is the same thing as the SDO. And RC2 is our storage clock signal, which is the same thing as the SS signal, as we just discussed. So all we really need to do is turn on the peripheral, make sure that the peripheral outputs are assigned to RC0, 1, and 2, and it should work. So looking at the pin allocation table under the MSSP column, we can see that SCK is already assigned to RC0. SDA and SDI are assigned to RC1. Neither of those is what we need. The one we need is SDO, which is unassigned right now. And this SS1, which is already attached to RC3, is not the one we need. The SS1 that's been assigned in this table is actually designated as the receiving client select, not for the outgoing, so we can completely ignore it. The SPI host uses standard GPIO pins. In other words, the serial port peripheral does not control the CS signal for outgoing connections. So all we need to do is assign this SDO signal a pin. And using the lookup table in the peripheral pin select module, the appropriate code for the SDO signal is 8. So we'll assign that value to RC1 PPS, which will assign RC1 to the serial data output. Alright, now here's the little bit that messed me up. So you can see how SCK1 has already been assigned of RC0. It should have worked, but it didn't. I spent hours trying to figure out what I was doing wrong, and I still don't know what I was doing wrong, but I did manage to figure out how to get it to work. I simply had to assign RC0 to the SCK output. But wait a minute, it should have already been assigned. It says so right here in the manual. Oh, I don't know why this is the case. I have no idea why I need to explicitly assign an output pin to something that should have already been defaulted, but assigning it works. Another thing we had to do is set the CKE configuration bit for the serial port. According to the datasheet, that means that transmit occurs on the transition from active to idle clock state. Yeah, I also didn't understand that. But I figured out that that was necessary because in the datasheet of the shift register, you might notice that all of the triggers occur on a rising clock edge. That's what these little arrows indicate. So every time we send a clock pulse from low to high, whatever value is sitting on the serial data output pin gets sent to the shift register. So in order to make sure that that data is sitting and ready, we need to put that data there when the clock transitions from high to low. And so I think that's the translation of this statement right here. Of course, I can't be entirely certain about that, but this setting works. So we can configure that in our code and then enable the serial port for SPI host mode. Finally, we can get rid of all this manual bit manipulation that we're doing here and replace it with this simple line to send our target intensity value directly into the serial port buffer, which will then automatically send out all 8 bits in sequence, which is exactly what we see when we program the chip. Well, kinda. It seems to work, but it appears to be shifted to the left by 3 bits. To understand why that is, let's take a look at the scope. And now it's obvious as to what's happening. We're triggering our storage register before the transmission is complete. That's because it takes time for the peripheral to send the data out. In our code, we're calling the subroutine and then immediately triggering the storage. We need to wait a little bit for those 8 bits to be sent and then trigger the storage. And for that, we can use an interrupt. Bit 1 of the PIE register has an interrupt for the MSSP peripheral. So all we need to do after we call our send subroutine is wait for the interrupt and then trigger the storage. So let's get rid of this line and then adjust this line to include a serial port interrupt. Then in our interrupt vector, test for that interrupt flag and call an appropriate handler. And finally, create that handler, which when called will clear the interrupt flag and trigger the storage. Now when we run it, it looks much better. And taking a look at our scope, we can see that it does indeed wait for the communication to end before triggering the storage. And if we take a quick measurement, we discover that it's about 34 microseconds, which is less than half the time of the manual bit manipulation we were doing previously. Okay, so far so good, but what we're actually displaying here on the indicator is not all that user-friendly. I mean, this is a binary count. I'd like to show something a little bit more visually appealing. How about a single dot that will go end to end depending on the intensity level? So to do that, when we call our send subroutine, instead of just sending the raw value, it needs to be transformed. So we're going to use another one of these common bank registers and initialize it to 1, which would be the rightmost LED on our indicator display. And just like before, we'll capture the target intensity, except this time, we're going to use that value as a shift counter to let us know how many times to move that dot. So first we'll have to test it to see if our target intensity is 0. And if it is, we're going to branch forward a little bit and simply output the 1 we had already prepared, because that 1 indicates the lowest intensity state. But if it's not, we're going to left shift that value once, and then decrement our counter, and continue shifting if our count hasn't completed. Then we'll capture the transformed indicator output and send it off onto our serial port. Now we can put in our missing branch value to make sure we go to the right place, and it kind of works as expected. You'll notice we do have our sliding dot, but it falls off either edge. Well, that's an easy fix. To prevent the dot from falling off either end, we just need to limit the range of our intensity. So over here in the rotary encoder interrupt routine, where we change that intensity, we can first test it to see if it's been decremented beyond 0 by simply testing if it's looped back to FF. And if it did, we increment it back to 0. Then we'll test to see if it's been incremented beyond the maximum. And to do that, we'll simply subtract the maximum value and see if the result is 0. And in that case, we simply decrement it back to its maximum. Now look at that! Our intensity is now constrained, so we can't have that dot fall off the edges. But of course, you saw that coming. Now we only have a maximum of 8 discrete levels of intensity. What if we want more? Well, rather than hard coding this value to 8, we could change this line and turn it into a constant called int max. And then up here in the top, we can define that int max as the number of discrete intensity levels, and then change it to hexadecimal 10, which is 16 intensity levels. But of course, we're going to need to do more. We only have 8 LEDs connected to this. We're going to need another 8. Well, remember in the datasheet of the shift register, there was this other pin here called Q7S. And in our schematic, we've deliberately left this unconnected. Well, that Q7S pin is actually the serial output, and we can connect the serial input of another shift register to the Q7S output. So the way this works is the first 8 bits of data will come in through the serial data input and sit in this first shift register. Then as soon as the 9th bit is received, the first bit that was sent gets pushed out of this Q7S pin, which leads to the data in of the second shift register. So by connecting them this way, we now have created a 16-bit shift register. And we can wire it up in exactly how it's written into our schematic, connect our additional 8 LEDs, and try to keep the wiring as neat as possible. That doesn't look quite right. It almost looks like a delayed copy of the first shift register. That's because we're still sending an 8-bit output. In order to fill the 16-bit shift register, we need to send a 16-bit output. Let's use this spreadsheet to describe the 8-bit output that we had previously. The possible values that we could output are from 0 to 7. Column B shows the appropriate LED which would be lit up based on those values. Column C shows the decimal representation of the output if it were a binary value, and column D shows the hexadecimal representation of the output. When we go to a 16-bit output, things get a little bit more interesting. Our intensity values range from 0 to 15, and we have 2 potential columns. Let's call them indicator banks for our outputs. If our intensity is between 0 and 7, then indicator bank 1 has to be completely clear. In other words, none of the LEDs in this indicator bank will be lit. But indicator bank 0 will have one of the LEDs lit depending on which intensity value we have. But for intensities between 8 and 15, indicator bank 1 will have a value and indicator bank 0 will be completely empty. And just like our 8-bit indicator, we need to send the most significant bit first, which means in all instances, this indicator bank will be sent first, followed by this indicator bank. So we're going to need another constant to hold the number of indicator banks that we have. I'm going to call it ind size for indicator size. And in this example, I'm going to use 4. Now, our physical breadboard only has 2 indicator banks on it for 16 bits, but on our worksheet, I'm going to use 4 just to demonstrate that we can do this in the general case. So that way, in the future, if we ever wanted to put 24 or 32 LEDs for our indicators, this technique should work for that as well. So once we've defined that indicator size, we then need to prepare what we're going to call a bank counter in our code. So let's do that. First, we'll add our ind size constant, and then define a general purpose register to hold that indicator bank counter. And then right after we calculate our intensity, I'm going to collect that counter and store it into my register. Notice how I decrement the value before storing it in the counter. That's because we want our constant to represent the actual number of banks that we have, but that variable is actually 0 based on our worksheet. So for a 2-bank indicator, in other words, a 16-bit indicator, the indicator bank numbers are going to be 1 and 0. Now in our original send subroutine, the first thing that we do is prep the minimum intensity state, which in this case is a 1. Now with multiple indicator banks, some of those banks will be empty, which means we can't pre-prepare the 1 as the lowest indicator state. So we've got to get rid of this code and replace it with this to clear the indicator bank. Now let's go back to our worksheet and iterate our first loop. Now in the instance we have 4 indicator banks. Our y variable, which is our indicator bank counter and is stored in GPR22, is going to start off as 3. And in this situation, intensity values from 0 to 23 should result in an empty indicator bank. Only indicator values from 24 to 31 will result in a value in the first indicator bank. So to do this, we need to define an expression. And after some thinking, I came up with this. Z0 equals x minus y times 8. If you calculate Z0 for values of x ranging from 0 to 31, you result with minus 24 to 7. Then we can test whenever Z0 is greater or equal to 0. Here's all the instances of x where that is true, and then calculate our final output by using 2 to the power of Z0. If you take the results in the highlighted box and convert them to binary, you will result with the output that we want. So we're going to need a way to put that expression into code, but before we do that, let's keep iterating these loops to see what happens. When we come into our second loop, y will be equal to 2. And if we apply the same expression, here are the results for Z0. Performing the same test and the final calculation, we get these results over here. Now right away, this doesn't look right. We know that these values are good, because when they get translated into binary, it will result in this output. But these values right here will also pass the test, which means our expression will process and calculate those values and send them. But what we want is a completely empty indicator bank. But actually, this isn't really a problem, because all of these numbers that are highlighted here are too big to fit in an 8-bit output, which means you can't actually display these numbers in an 8-bit output. If your 8-bit window is over here, those numbers are over here somewhere, which means the end result will still be an empty indicator bank. So practically speaking, we still will get this empty bank here. And the same thing applies for the third loop and the fourth loop. So technically, this expression is enough. But the way our microcontroller will process this expression, this 2 to the power of Z0, it has to create a loop and then left shift the value a number of times, which takes time for values that aren't even going to be displayed. So ideally, we want to avoid the processor taking that time to perform this unnecessary calculation. So we're going to need another expression. And that expression is this one. After we test if Z0 is greater than or equal to 0, we're going to test if Z0 is less than 8. And you can see for the first loop, it passes all the way through. All of these values are less than 8. However, once we get to the second loop, only these values are less than 8. And then this test will fail. which means that these values will not get processed, and the only values it gets processed and sent are these ones over here. And that'll work for the third loop and the fourth loop. Notice I kind of have a fifth loop over here too. Well, that's because we haven't created the code to stop looping. That's another expression that we need to test. And that test is right here. Every time we enter the loop, we need to test if y is greater or equal to 0. So for the first loop, which would be y equals 3, that is true. For the second loop, it will also pass all the way until we get to the fifth loop, where it will fail and stop, because y here equals -1. Okay, we're almost ready to take that expression and turn it into code for our program, but we have one more challenge in front of us. This expression, z0 equals x minus y times 8, is really difficult to put into assembly code. That's because the instruction set for our PIC microcontroller has the basics like add and subtract. It can even do the 2 to the power ofs by using the left shift instruction. But there is no multiplication instruction. So although we could put the work in to turn this expression into something more assembly friendly, it might be easier to change the expression to remove the multiplication bit. And we can do that by adjusting our y variable. See, this y variable or bank counter currently decrements by 1 each time. So it goes from 4, 3, 2, 1, 0, or in our case, our 16-bit indicator would be 1, 0. It doesn't have to increment by 1. We could have it increment by 8. So if we did that, rather than starting at 3, we can start at 24. Then with each bank, we decrement 8, which brings us down to 16, which brings us down to 8, and then brings us down to 0. The indicator size would have to be adjusted to 32 rather than the 4 we had here earlier. And if we do that, then our Z0 expression simplifies to just x minus y. Now that is something that the PIC instruction set can handle easily. And you'll notice that the calculations still result in the same numbers that we had before, which means our output is unchanged, but the way we got there is much more efficient. So let's start making some of these changes. First, I'm going to adjust our ind size constant. I need to put the translation in the comments. So if we want an 8-bit indicator size, we have to enter the value 8. In our worksheet, we were using a 32-bit indicator size. So we would put 32 in the ind size, which equals hexadecimal 20. But for us, I want to use a 16-bit indicator, which equals a hexadecimal 10. And notice now how the ind size and int max constants match. That's a little side effect, which makes me internally very happy. Next, we'll come down to where that intensity is calculated, and rather than decrementing the indicator by 1, I'm going to decrement it by 8 before I store it in my counter register. Did you notice how I included an option to disable the indicator as well? Yeah, right here, check that out. If we put a 0, that means the indicator size is disabled. See, we may not always have an indicator, so I wanted to put something in that would tell the code to just skip all those unnecessary calculations for that case. So to test that, we're going to temporarily add 8 to our indicator bank counter and test if it equals 0. In the case that it does, we'll branch forward 2 lines and skip the send subroutine entirely. Now in the case that it doesn't, we are going to go into the send subroutine. So after preparing an empty intensity state, we can then immediately make this calculation. And these 2 lines do exactly that. Then we test the result. And if the target intensity is within the current indicator bank, we're going to skip this line and start processing. But we can't start the shifting yet because we have to perform this test. Z0 is less than 8. So first we're going to store our Z0 value into the CBR71 and then subtract 8 from it. Then test if the current intensity is beyond the current indicator bank. If it is, then we need to output an empty intensity state. So to do that, we'll just branch forward to this line over here. And now we know the current indicator bank needs to have a value, so we begin the processing. First, we'll check if the target intensity is 0, in which case we want to output the lowest intensity state. And to do that, we have to increment the current empty intensity state by 1. And if it wasn't 0, we can perform the shifting. But even in that situation, we still need to start with a 1 as the lowest intensity state. Now that we have all the lines of code, I can go back and adjust these branch targets to make sure that they end up in the right locations, and add one final branch to simply skip the increment if we've already completed the left shifting. Now the final thing we need to do is adjust the interrupt handler, because remember, even though we're creating a 16-bit value to send, this serial port peripheral still only sends 8 bits at a time. So we need to listen for when the interrupt is triggered, and when it is, test to make sure that there's still more data to be sent and then send that data. So let's go make the change to the interrupt handler. So currently our interrupt handler will instantly trigger the storage. Instead, we need to test our indicator bank counter. And in the situation when it is 0, we want to branch forward and trigger the storage for the final output. But in the situation it's not, we need to decrement that counter by 8 and then call the send subroutine again. Okay, that was a lot of code. Let's run it and see if it works. Oh, isn't that spectacular? Look at that. A full 16-bit indicator, bounded by its extents, the dot's not dropping off, and it is incredibly responsive. And based on the way we designed this should also work for 24-bit, 32-bit, whatever size indicator that we want. All we have to do is edit these values over here. For fun, let's try changing this to an 8-bit indicator with an 8-bit intensity maximum. Okay, so at first, it kind of looks like it doesn't work. But actually it does, because we've told the code that there's only one shift register. So actually what we should be seeing is this. I'm covering the other indicator bank with my finger because we would never see it anyways. So in actuality, this is working just fine. We can set our intensity maximum to any value we like. How about hexadecimal A, which is 10 discrete levels of intensity? Look at that. It can't exceed the 10th LED. It's perfect. Let's try E, which is 14. There you go. I can't exceed the 14th LED. Now what if we disable it outright, bring it down to 0? And with it disabled, the rotary encoder does nothing to my indicator. But I'm still seeing one lit. Well, it's lit because the shift register still has that value stored in its memory and our controller has done nothing to clear it. In fact, even on startup, if I cut the power and then bring the power back on, you'll notice that the indicators sometimes are lit entirely and sometimes not lit at all. That's because when we cycle the power to the shift registers, the value that's currently sitting in the shift register is, well, random. We can't determine it unless we reset it. See, we kind of skipped over these pins the first time we set up our shift register. There is a storage and shift reset pin available. And currently, both of those pins on both of these shift registers are tied high. And they need to be high for normal operation. Bringing them low resets or clears the shift register. So what we really need to do is start with those pins low and then bring them high after some time. And we can do that by connecting all of those pins to an RC circuit, resistor to high and capacitor to ground. Connecting the pins this way means that we're going to reset the shift registers upon startup. So it will start at ground. And after some time, will then be raised high for normal operation. And the time it takes for it to go from ground to high is dependent on the value of the capacitor and the resistor. So the big question is, what values do we use to get the right time? Well, we need to hold the resets low long enough to make sure that the shift register is reset. And looking through this datasheet, I could not determine what that value is. However, I did discover that these particular shift registers are really, really fast. And peppered through the datasheet are all sorts of parameters indicating how long things take. There was one parameter in particular called propagation delay. And the highest propagation delay I could find is 225 nanoseconds, which is incredibly fast. So as long as we keep it low for at least 1 millisecond, I'm confident we should be fine. So how long do we actually hold it low? Well, for that, I had to look up how long the startup takes for this microcontroller, and it really wasn't all that helpful. It gives us these graphs, but not any values to go along with it. Except that it kinda does. See, I couldn't figure out under normal circumstances how long it takes for the microcontroller to start up, but I did discover that there is a way to define the startup time. See, there is one particular configuration in the device that allows us to control the power-up time. And by default, it is disabled. But if we set the value to 2, then we can set that power-up time to 64 milliseconds. Well, now we have something to work with. So as long as we choose our capacitor and resistor such that the hold time is between 1 and 64 milliseconds, and then enable this little power-up timer on our microcontroller, we should be in good shape. So to enable the power-up timer for our microcontroller, I'll simply add a PWRTS equals 2 to our config words. Then I'm going to choose a capacitor based on most of the other capacitors I have in my circuit. And that happens to be a 0.1 microfarad capacitor, super plentiful, let's use it. And then perform a calculation. Our time constant basically is the resistor times the capacitor. So given a minimum time of 1 millisecond, the minimum resistor value works out to 10 kiloohms. And given a maximum time constant of 64 milliseconds, the maximum resistor we want is 640 kiloohms. To refine this a little bit more, our minimum time constant actually should be multiplied by 5, because 5 times a time constant is generally accepted as the final level. So in other words, we have a minimum of 50 kiloohms and a maximum of 640 kiloohms. Well, I happen to have a lot of 100 kiloohm resistors. Let's go with that. So all we're going to do is make sure that all the reset pins are tied together and then connected through this resistor to power and that capacitor to ground. Now, as we start it up, no matter how many times we do it, notice all the LEDs are always off. Okay, so that's a step in the right direction. The shift registers are being cleared and reset with every power cycle, but we don't want this to start up with all of the indicators off. We want the rightmost indicator on, which would indicate the lowest intensity level. So to do that, all we need to do is send that minimum intensity level on initialization each time we start up. And of course, the value of that minimum intensity is always going to be 0, hence the clear F. Now that is much better. I can power cycle the system and the indicator will always start at the lowest intensity level. Even if I hit my reset button without a power cycle, I'm still starting at the lowest intensity level. This works perfectly. Alright, so we've leveraged the SPI mode of the serial port peripheral on the PIC microcontroller to control an arbitrary number of shift registers to display an arbitrary number of LEDs to indicate any level of intensity for our illumination system. Wow, and we did that with using only 3 pins on our microcontroller. Incredible. Now let's see if we can do the same thing on the input side. One of the things we're going to do on our next episode is we're going to re-enable that button and then explore the use of adding additional buttons onto our system, all by using that one single pin. And in order to do that, we're going to have to dive into analog detection. So, see you next time.